Okay, let me share my screen. Okay, so you can see my slides, right?
Yes, we can see that.
Okay, so thank you for the introduction. Again, I'm Pablo Vizcaíno. I'm a PhD student at the Barcelona Supercomputing Center. And in this technical session, I will present RAVE, which is a QEMU tracing plugin for RISC-V vector executions. The outline that we're going to follow is divided into two parts. In the first part, I will cover the background of the RISC-V vector extension, or RVV for short. What is the EPAC chip? What is the simulation environment that we have? Why do we need RAVE? How does RAVE work? And then some performance and use cases of RAVE. Then I will let you ask any question that you may have. And I will jump into the second half of the session, which will be a live demo of how do we use RAVE at BSc to analyze vector executions. So as you may know, RVV is the RISC-V vector extension, which is the RISC-V approach for the high-performance computing for HPC. Right now in the market, there are many vector extensions. They can be very short, of 128 bits, up to 16,000 bits for the NEC vector extension, or up to 2,000 bits for the ARM scalable vector extension. When I say up to, it's because we also differentiate between ISA-defined maximum vector length and implementation-defined maximum vector length. On the family on the left side of the screen, it's the ISA-defined maximum vector length, which means that if you are a developer at Intel and you are making a chip and you decide to use AVX 512, your vectors will be always 512 bits. But if you pay some royalties to ARM and you build your own chip with SVE, you can decide if your vectors are 128 bits or are 1,000 bits or up to 2,000 bits wide. With RVV, this goes even further. The upper limit is not defined. I believe it's 2 to the power of 32, or it's basically infinite. So whatever, as much silicon as you have, and that's what differentiates with the implementation-defined maximum vector length. There's another concept that I will be using during this presentation, and it's important to grasp, which is the runtime variable vector length. With the RISC-V vector extension and the NEC vector extension, you have this property. Let me show you with an example. On a scalar processor, if you want to add two arrays together of 10 elements, you would do 10 additions. If you want to do this with a SIMD extension, for example, with AVX2, which can have 4 double precision elements on each instruction, you will do one instruction with 4 elements, another instruction with 4 elements, and then the last 2 will be done with scalar instructions. With a variable vector length, like for example, RVV or the NEC vector extension, you can have one instruction with 4 elements, another instruction with 4 elements, and then another vector instruction with only, for example, 2 elements, or any arbitrary number between 1 and the maximum of the machine. So the hardware is adapting itself to the software. That being said, who is actually implementing this technology? So one of the first adopters of the RISC-V vector extension is the EPI project, the European Processor Initiative. You might have heard of it, which has two main develop lines. One is the REA, which is making an ARM-based general-purpose CPU. This has nothing to do with RISC-V. But then it has the EPAC, the European Processor Accelerator. This is an accelerator completely based on RISC-V, which has many acceleration tiles, but we're going to focus on the VEC one. VEC is composed of a CPU and a BPU, with the particularity of having a very large vector length on the BPU. The vector processing unit has up to 16,000 bits per vector. This means 256 double precision elements per each vector. This picture here is at a scale. So with Intel, you can go up to these 8 elements per vector. With SVE, you could go up to 2,000. We are on this range. So we are on a completely different scale than Intel or ARM, on a very similar to the NEC vector extension, if you are familiar with that architecture. So by now, I'm sure you are already eager to try this EPAC accelerator. It sounds very exciting, but how can you actually try it? So BSc has the software development vehicles, the SDVs for short. These are a set of hardware and software tools that help you to port your applications or port your software to these new and hardware prototypes. Imagine you have some Fortran, C or C++ code. What you can do is compile it using our LLVM-based compiler, which will vectorize your code. And then you can choose between two routes, where you can choose or you can do both. One is doing hardware, so FPGA, this is hardware emulation, or running on the actual test chip that we have of the EPAC. This is real silicon printed running these very long vectors. Or you can also go the other way and go with software emulation. Right now in the project, what we do is we have some Sci-Fi Unmatch boards. I don't know if you heard of them, but they are scalar RISC-V boards that you can buy on Alibaba. And on there, we run Behave, which is a software emulator program that emulates the vector part of the applications. Then when you have executed your application either on the hardware or either on emulation, you can analyze the vectorization using some profile tools that we have at BSc. So if this is clear and you want to try it out, what problems you might encounter? Well, you can compile your code because the compiler is open access. That's fine. You can analyze your executions because the profiling tools are also open access. But how do you get these traces and profiles of your applications? You cannot run on the hardware because right now the access is restricted to the API partners. This is a project that's still ongoing, so the hardware is not open. And you could technically go with software emulation, but you require a RISC-V board. If you're attending this seminar, I assume you have interest in RISC-V, so you might have a RISC-V board, but I'm sure that many of you don't have access to RISC-V boards. So this is open access, but it's a difficult access, I would say. There's another problem with the software emulation that we have on the project, which is Behave. This is the software running on the Unmatch boards. So let me show you how it works to understand what are the problems. You have a vectorized binary that you run on a scalar core. So scalar instructions are run until there's a vector instruction. When there's a vector instruction, the core cannot execute it because the core is a scalar one, and it raises an illegal instruction signal. Then Behave captures that signals, emulates the vector instruction, and goes back to the user code. Then you find another vector instruction, and you go back to Behave, and so on and so on. What are the problems here? First, portability. As I said, you need a RISC-V hardware to run the scalar instructions. Then functionality. Behave only exists in the context of the vector instructions. So it cannot see the scalar instructions or anything outside the single vector instructions. And then there's the problem of speed. Each time you have a vector instruction, you are going in the operating system because this is an exception. Then you are jumping to Behave, then jumping back to the operating system and back to the user code. So this can go very slowly, very fast. So what is the alternative to this? Well, it's using QEMU. At the start of the project, QEMU did not support the RISC-V vector extension. That's why Behave was created. But now, 2024, QEMU supports RBB. And QEMU solves the three problems that I just mentioned. It's portable. QEMU can run on your laptop, whether it's x86 or ARM or whatever, it will run QEMU. The functionality is also solved because QEMU has visibility of both the scalar and the vector instructions. So you have complete visibility of the application, and you can use plugins. We will go into that in a minute to generate any kind of metrics you want. The plugin attaches to the simulation, and for example, it can count memory access, or it can count vector instruction. It can count whatever you want. And then the speed. I don't know if you know this, but the Q from QEMU comes from quick. QEMU is the quick emulator. So it's actually quite a lightweight and fast emulator that can run on very fast systems. So it can outperform the previous simulation method. That being said, we needed to make some changes to QEMU to adapt to our architecture. The first one is very straightforward. By default, the maximum vector length that the RISC-V CPU or emulated CPU of QEMU has is 1024 bits. We just needed to change this to the EPAC value, which is 16,000 bits. And then the second change needs a little bit more of an explanation. So how does QEMU work on a very, very, very high level? You have your code, which QEMU translates into blocks of instructions. So for example, in this code, we have two loops. One has a vector length of 256 because it has 256 iterations. Another has a vector length of 8 because it has a vector loop length of 8. I have coded this with green for 256 and red for 8. These are the vector loads, vector additions. This is the assembly, but you don't need to look at it. So how does QEMU works? It simulates a whole block of instructions, and then it sends that block to the plugin, which will analyze the instructions, and the plugin does whatever you want it to do. What will actually happen is that the vector length will be set to 256. It will execute some instructions, then the vector length will be set to 8, and it will execute other instructions. That's what I meant with a variable vector length and some 4 to 5 slides ago. Then when it's the turn of the plugin to run, it will analyze the block, it will try to query or to read this vector length control register, and it will read an 8 because it's the last value that has been written. And it will say, okay, these instructions have all been executed with vector length equal to 8. And that's not the case. The first ones were executed with a much larger vector length. So the quick fix that we did was limit the translation block to one instruction, so we don't have this kind of inconsistency problems. Of course, this can be optimized in the future to more selectively changing the size of the block, but this is a conservative measure that works for us at this point. Then we actually need to write the plugin, which is RAVE. RAVE is the plugin that runs on QEMU to measure and evaluate and analyze the vector execution. We want our plugin, RAVE, to match the functionalities of Behave. Behave is the older simulation method that we had at the API project. These are mainly printing the sequence of vector instructions of the emulated binary. And for each instruction, report what is the vector length of the instruction, what is the element width, which registers are being used, and any kind of information that you can imagine related to the instruction. Behave also provided an API that could be called from the emulated application to differentiate between different instrumented regions in the code, so zones of interest, start tracing, stop tracing, and this kind of APIs. And finally, we also wanted to print PRV traces. PRV is the format for Paraver. I don't know if you heard, but Paraver is a tool to visualize traces that we have at Paraver. We will go into that also in a few slides. Don't worry if you don't catch it now. Additionally, we want to extend the functionalities of Behave. Mainly, we want to also count the scalar instructions. This is something that could not be done with Behave, but we can do it with RAVE. We want to compute vectorization metrics on the different instrumented blocks that the user can instrument. And at the end of the emulation, we want to generate a report that summarizes these vector metrics. You will see an example in a few slides. So to generate this kind of metrics, what we did was classify the instructions following this diagram. We have the total instructions, which we divide into scalar, vector, and setBL. setBL are all those instructions that control the vector length of the machine. And then the vector instructions are further divided into arithmetic, mask, memory, and other, and the arithmetic into integer and floating point, and the memory into the 3 different access modes that we have on the vector unit. Once we have this classification done, you can derive as much metrics as you want. For example, we derive the vector mix. This is number of vector instructions divided by total amount of the instructions. Or the vector flops per byte, that is the number of floating point arithmetic vector instructions divided by the vector memory instructions. Whatever combination you can imagine, once you have this tree, you can compute it. So the API. As I said, we want a method to the application to talk to RAVE, to instrument different zones of interest in the code, and so on. But we have a problem. Emulation is completely transparent to applications. The application does not know that it's being emulated, so it cannot talk with QEMU or with RAVE. So RAVE inside QEMU is only seeing the simulated instructions, nothing more. So we must find a way to communicate through these instructions, but without changing the program behavior. To do so, what we do is use instructions that write to the X0 register. If you know a little bit of hardware, normally the X0 register is always hard-coded to 0, so adding these instructions will not alter the system state. To give you an example, we want to define a function that the user can write in his code, which is RAVE start trace. And to do so, we arbitrarily encoded into this instruction that writes to x0 with a -3. And when RAVE is evaluating the translated instructions and it finds this instruction, he knows, okay, this instruction is not a normal instruction. This has been put by the user to indicate that I need to start tracing. The same for the stop and the same for the restart. We also want to have a more complex API because we want to add some instrumentation mechanisms to define what is said about regions of interest. Let me show you with an example. We want to define tuples of events and values. For example, one event can be code region, and the values can be the different regions in your code. Then the user, he has his main function in his code, and he says, okay, event number 1000, this is arbitrary, but we normally use 1000, is code region. Value 1 within this 1000 is the zone ini. Value 2 is the zone compute. And you can add as much as you want. Then on the actual code, you have to enclose your functions or your zones of interest with these calls to RAVE, which are encoding, okay, here the zone 1 is starting. Here the zone 2 is starting. And with the 0, it's ending. And then you can get this kind of traces where you can see with different colors the different regions of your code, how long do they take to execute, and so on. That's what we mean with API and instrumentation. To encode these events and values function calls of the API, we also use the same mechanism. We are writing to x0 with different instructions meaning different things. With an OR, we are saying that we are putting an event and a value. When we want to assign a name to an event, it's a little bit more complicated because we need to pass the individual characters in the string, but it's more of the same. It's just putting instructions that don't change the program behavior, but that RAVE can see, it can identify, and it can do different things depending on the pattern. It's just inventing a very easy protocol. So this is the plugin flow. So what is the pseudocode of what the plugin is doing? It's iterating through the instructions in a translation block. As I mentioned, this translation block is just one instruction by now, but it's expected to grow. Then it disassembles the instruction, and depending on the type of the instruction, it does different things. For scalar and vector instructions, it fills a structure with the program counter, the destination and source registers, the type of the instruction, and all of these things. And then it assigns a callback function. So each time this instruction is simulated, this callback is called. For API and tracing instructions, it assigns different functions depending on their on what we want it to do. If it's the restart trace, so it restarts the trace. If it's the stop trace, it stops the trace. Whatever function we wanted to assign. Then this is the callback function that vector and scalar instructions execute within the RAVE plugin. Vector instructions read the CPU state, so they need to read the vector length and the vector C and all of that. And then they just lock the instruction to a log file and trace it to a trace file. And then you need to increment the counters of the simulation. These are related to this tree that I showed you before. So if it's a vector instruction, we increase the vector instruction counter. If it's a memory instruction, we increase the vector memory, and so on. It's pretty straightforward what this callback does. So once we have defined why do we need RAVE and how does RAVE work, we wanted to evaluate it. To do so, we found 4 different configurations or setups. First, we have the commodity laptop. This is the same laptop that I'm doing the presentation now, which we run QEMU and RAVE. Then we have a high-end AMD node, which is also running the same QEMU and RAVE. And then we have 2 different setups, which is the unmatched RISC-V board running Behave. Behave is the older simulation method that we had. And then native execution on the FPGA, which is an FPGA that is implementing the actual hardware, the EPAC of the very long vectors and all of that on an FPGA. It's running at 50 megahertz because FPGAs are very limited in terms of frequency, but it's another way of running vector binaries. These 3 here are software emulation. This here is hardware emulation. So let me guide you through these 3 plots. the first thing that we did was run a synthetic benchmark. This synthetic benchmark is increasing the number of vector instructions per million instructions. It has a loop with very easy instructions, but on the horizontal axis, what you can see is how the vector instructions per million instructions, so the ratio, is increasing. Then on the vertical axis, you see the simulation time or the execution time of the 4 different methods. And you have 3 plots. The plot on the left is only running the simulation. The plot in the middle is generating a log file also. And the plot on the right is generating a Paraver trace. What you can see is that the behave, which is on purple, has a very different trend as the other methods, because as the vector instructions increase, the performance degrades. It takes longer and longer to simulate. This is related with what I showed you before about having to enter and exit the operating system each time there's a vector instructions. So more vector instructions, more operating system overhead, and yeah, you can see that the performance degrades. You can also see that the AMD node running QEMU and RAVE outperforms behave from a very early point. This is 0.015% vector instructions, or 150 per million. And this point gets even more to the left when you start doing more complex things like generating a log file. Another interesting note is that the FPGA native execution, which is only present on the left plot, because on the FPGA we can run binaries, but we cannot generate log file or Paraver traces in the same fashion as we generate with QEMU. We can generate other type of traces, but they do not have the same granularity and the same length of the traces that we generate with QEMU. So it wouldn't make sense to put it in this plot. But you can see that even going at 50 megahertz, we are not that far away from other systems that are simulated on the gigahertz range. So yeah, it's slower, but it's actually not that slow than software emulation. Then what we did was running actual applications, not a synthetic benchmark. And here we see some interesting things. So again, we have the same 3 plots, running, log file, Paraver, the same 4 lines, laptop, AMD, Unmatched, and FPGA. And you can see 2 different trends. For these 3 algorithms, which are the breadth first search, connected components, and single source shortest path, these are graph algorithms, behave, which is this small purple line, is actually faster than the other alternatives because it has the fewest seconds to run. That's because the graph applications need a lot of instructions to just read the graph from the disk. And this is an intrinsically scalar operation that is not vectorized, so behave is faster than QEMU. You could say that we are on this range here with very, very few vector instructions per million. Then you can see that for the other algorithms, which are more compute-bound or not compute-bound, but doesn't have to read data from the disk and everything, the QEMU, either on the laptop or on the AMD, on blue and orange, is faster than both behave and the native execution. As a quick note, on the GEM, so this is a matrix-matrix multiplication, running with the FPGA is actually much faster than behave, because this is very, very, very compute-bound kernel. You can see that when we generate a log file, these differences are smaller, and when we generate a Paraver trace, QEMU always wins against the older simulator method behave. So I showed you that RAVE and QEMU is fast, but I did not show you that it's useful. This slide has a lot of colors and a lot of things, so let me guide you through it. These are screenshots from Paraver. When I talked about Paraver traces, I meant this slide. And what you can see here is a sequence of the different instrumented code regions. So this is a region that the user decided to isolate. These are another region that is actually repeated a bunch of times because these are color-coded. And what you have here below it is another timeline. In this case, it has 2 lines. One has the scalar instructions, another has the vector instructions. This already gives you a feel of which regions are vectorized and which regions are not vectorized. For example, because these 2 lines are synchronized. So this magenta region has very few vector instructions. They are like sparsely distributed among the region, but this red region has a lot of color here, so that's vector instructions. You can zoom in on this line, on this timeline. This is this picture here, and you can actually see the different scalar instructions and then the vector instructions with different colors. Maybe I don't know about memory, but the light green is a load, the dark brown is an addition. They are color coded. So you can actually see the compiler, how it's scheduling. So it's having some scalar instruction, then some vector with some scalar in between, and you can kind of study what's the behavior of the compiler. You can also get some tables. For example, here we have the proportion of scalar and vector instructions. This means that for the red phase, this red phase on the top, you have 63% of the instructions being scalar and 37% being vector. But for example, for this magenta step, which is called TD, but this is not relevant now, virtually all the instructions, 100% of them are scalar. These vectors are so few that they don't even have more than 2 decimal places. You can also get this kind of tables on the bottom where you have the recount of how many instructions of each type are executed. This is for the phase init. Init is the white phase on here on the start. And you can see that you have 128 vector subtraction. We have 256 vector loads. We have 128 vector indexed stores. This is the assembly of the vector instructions. And you can also see the vector length of those instructions. For example, in this case, for the init phase, all the instructions are at the maximum vector length of the machine, or nearly the maximum, which is 16,000 bits. Then you can also use these Paraver traces to track the changes in your code. So for example, here is what we just saw about this magenta phase having very few vector instructions. We changed the code and we managed to vectorize it. And now there are many more vector instructions, which you can clearly see when you look at the Paraver tracers. There's a lot of more color here on the vector timeline and also on the tables. Now it's 16% of the instructions are vector, when back then it was 0%. So RAVE is useful to track this kind of changes and easily visualize this kind of changes to the code, to the compiler, to the infrastructure, and all of that. Finally, if you don't like colors and you don't like Paraver for whatever reason, you can also work in your terminal. So RAVE is also getting this report at the end of your execution. Here you can see how you execute RAVE. You just put RAVE and then your binary. And you get this kind of information. For example, for the phase 3, this is the bottom-up phase, you have this many instructions, 45% of them are vector, this is the average vector length, you can get how many of those are arithmetic, memory, all this kind of profile. Then you can also change your code. For example, here we saw that we had many instructions regarding masks and other instructions. We changed the code and this number decreased. So you don't need to open Paraver or open the trace. You can quickly iterate through your code and see the changes that your changes in the compiler or changes in the code are doing to the execution. So to conclude this first part of the tutorial of the session, so we showed you how we developed the plugin for QEMU that is targeting this RISC-V vector extension. We also improved the simulation framework of the API project because we made it more accessible. You can run it on your laptop. It's faster than Behave, as I showed you in the previous plots, and the functionality is increased because you can see the scalar instructions. You can do many more things that you could with Behave. Also, I want to note that RAVE is already a reality. It's being used actively by the performance analysts at BSc, but there's still a lot of future work to do. We want to increase the block size, which I said that we limit to 1. This can easily be increased, and this will speed up the plugin. But also we want to add more and more functionalities. For example, we want to add multi-core emulation, so you can have traces of OMP plus vectors and see how the different cores are interacting with one another and with vectorization. We also want to add automatic instrumentation. This means that you don't need to manually instrument your code, but RAVE it can detect zones of interest because they have a lot of instructions or this kind of automatic features. And whatever else that we can imagine. It's a continuous work in progress. So with this slide, I end the first part of the talk, which was presenting you RAVE. Then on the second part, I will be doing a live demo of how do we actually use RAVE to get the traces, to emulate, and all of that. But if you have any question about what I just presented, that would be a great time to share your questions.
There is one question from Paul Clark. Paul, you are allowed to unmute yourself if you would like to ask that verbally.
Thanks, Rafael. I think I may have answered my question. So at the towards the beginning of your implementation, you showed that there's a way of associating a name with a region, and then in the yes, that right, RAVE name event. And then later in that graph, actually above, you have different regions of different colors, and those different regions are associated with a name, right?
Yes.
And then in Paraver output, you displayed a little bit later. It actually had statistics for each region, and that's all basically, yeah, that right there. That's all those names. So you set those names in your program?
Exactly. So you set the names, the colors are assigned pseudo randomly by Paraver, but the names are what you set on your program. Yes.
Okay, that answers my question. Thank you.
No problem. Thank you for the question. So
anyone would like to ask a question verbally, just raise your virtual hand and I can allow you to speak. I think if you do not have any other question, I think we can. Oh, one question. No, it's about recording, so don't worry. I think we can move on to the second part. Okay. So for the second part, I will show you how do we actually use RAVE, and we will see how we instrument, and it will be much clearer, I would imagine. So let me first introduce the code that I'm going to use for this demo. This code is represented by this diagram. It has an initialization phase. Then it performs 10 time steps, which has a call to the step function. You will see this in the source code in a minute, but just to have a general idea. And the step function is operating on some pressures array, then some temperatures array, volumes array, and then there's the compute delta function. Don't be fooled, this is not a real code. This is just something that I wrote that does some matrix operation, reductions, and all of that. But it resembles a real application, but it's not physically meaningful. It's just for demonstration purposes because it's short, it's easy to port, and it's nice to show you how RAVE works. So normally we have a first step when we do this demo, which is running on commercial RISC-V boards, only the scalar part of the algorithm and all of that. I'm going to skip that for this session because we are more focused on the emulation and RAVE and vectorization. So let me jump to this second part, which is vectorizing the application, emulating it with RAVE, and try to increase and optimize the vectorization with the insight that RAVE gives us. So let me jump to my laptop. You can see that, I believe. So let me show you the code that I just talked about. I will make it a little bit smaller. So this is the main function with the time step loop. This is the 10 time steps that I just mentioned. This is the step function. This is the compute delta function. And if we go inside the step function, we have the update to the pressures array, the updates to the temperatures array, and the update to the volumes array. This is what I just showed you in a diagram, but with real code. So you can, this is my laptop. This is an Intel laptop, so this is not RISC-V. I would like to have a RISC-V laptop, but I do not. You can compile or cross-compile this code with our Clang LLVM-based compiler, but you will not be able to run this binary because this is a RISC-V binary. This is my Intel laptop. This cannot be run. What you can do is put RAVE before it, and then the binary runs. Of course, this is not giving us much information. You can, of course, also compile with vectors. As you can see now, the compiler is very verbose, and it's telling you, oh, I'm vectorizing this loop. I'm not vectorizing this other loop. We will go into this message in a minute. But, of course, you can also run this. Let me make this bigger. We can also run this vector binary and RAVE emulate it. But of course, this doesn't give us much information.
So what you can do is instrument the code. In this source, let me go to the main function. You can see how we have this RAVE name event, RAVE name value. This is what I showed you in the previous presentation. In this case, I'm going to define 4 main regions, which is the pressures update, temperatures updates, volumes, and delta. And then 0 is everything else, so other. And you can see on the code right here how we, for example, this is the pressures update. So we enclose it with this RAVE event and value 1. Then the temperature is enclosed with the RAVE event and value 2, and so on. So this is the only instrumentation that we add. We can compile this version, instrument, and then if we execute it with RAVE, so this is called, let me show you. Okay, RAVE reference back instrument. And we ask RAVE to print the report. You will see how, let me go to the top. Well, you can see how there are a lot of information because it does 10 iterations, but you can see the different regions of the code. For example, this is the delta region. And here you can see, again, scalar instructions, vector instructions, arithmetic memory, and so on. And this already gives you a feel of how this is working. For example, the volumes phase, which is this one, this is not vectorized. You can see that 100% of the instructions are scalar instructions. So this already gives us a feel that something went wrong. But we can also generate a trace. We can do RAVE PRV name is equal to, let's call this reference back. This will run again, but now we have these traces here. We can open these traces with Paraver. They will take a few seconds to open, and then we can see the information that I showed you before. So for example, we can see, let me zoom into this. So I don't know if you can see that I zoom in, but
yeah, we can.
Okay, so here you have this pressure. Let me zoom here. Pressures, temperatures, volume. This small purple is delta, and then again pressures, volume, temperatures, because this is an iterative program. So you can already see that. You can also load the instruction timeline, for example. Let me make this bigger. And let me make this bigger here. We can synchronize them. Now they are synchronized. So for example, we can zoom in on here, and you can see this pressures phase, 0 vector instructions. This temperatures phase, it has a lot of vector instructions. This volumes phase on red, 0. And this is small purple one, delta, it has vector instructions. Of course, we can also open these tables that I showed you before. And this says temperature has this many scalar instructions. Let me zoom in, and we will see this much clearer. So temperatures have this many scalar instructions, this many vector instructions. Pressures and volumes have 0 and 0. And here you have the relative numbers. So 7% vector instructions, 93% scalar, 100% pressure, 0 vector, and so on. Okay, so that's the initial thing that you can see. And now, thanks to RAVE, you know that these two functions don't have many vector instructions. How can we fix this? We can go back to our terminal. Let me compile again the code. Just let me do this. We compile again, and let's see let me make this smaller, the compiler output. Here you can see, a little bit higher, yeah. Here you can see that the compiler is saying, I'm not vectorizing this loop not vectorized, because there's a call instruction within the loop. It actually says that there's a function call to the kube root of whatever value, so you cannot vectorize a function call. And then there's another loop that's not being vectorized, another important loop, which is this one, which says loop not vectorized cannot identify array bounds. So let me switch to the slides for a second. This will help. So these are the two messages that I just shown you: the call instruction that cannot be vectorized and the array bounds. And actually, in the code, you have here this kubroot. And what you can do is identify that there's two different kind of work in that loop, which is doing this whatever kubroot function and then some arithmetic. What you can do is separate it into two loops. One loop is doing the kubroot, another loop is doing the arithmetic. So it's not ideal, but at least this loop on the bottom will vectorize, even if this on the top doesn't vectorize. So sometimes fragmenting the loops helps in vectorizing. You can also note that we added a new region 5, because we want to differentiate between the different between these two loops. For the volumes phase, which the compiler said that it cannot identify array bounds, what we actually have is that we have an indirection. You can see that the precious array is being indexed by the bounds array. So it's an indirect access. This can sometimes scare a little bit the compiler. So there are two ways to fix it. One is adding a pragma on top of the loop. So it's just a message to the compiler or a hint saying, this is perfectly fine to vectorize, go ahead, don't be scared. But there's another way that it's making the pointers restrict. When you make a pointer restrict, you are telling the compiler that they do not overlap with one another. So the compiler is more free to do optimizations, such as vectorizing them. So you can see that these changes are done on the reference, beam increase vectorization. You can see it here. So this is separated into two loops, and the pointers here are marked as restrict. Also, there's another thing that I did not mention, that was that the temperature, let me go back to the slides. So I don't have it open, right? Okay. So the temperatures function it had vector instructions, but not so much. It was at 7%, if I'm not mistaken. We can actually see it. So look here, this is the temperatures function. It had around 7% of vector instruction. This is nice because it's not a 0, but it's still low. So we also want to increase that. And the thing is that when you look at the code of the temperatures, it doesn't have function calls, it doesn't have indirection, so it should vectorize. When this happens, the only thing that we can do is add some pragmas to tell the compiler that everything will be okay, make the pointer restrict, which we already did for the other optimization. And there's also a thing that's when there are limits in the loops that are known at compile time, put them on defines or put them on constant values or an equivalent to that, so the compiler has an easier time vectorizing it. So I just wanted to mention this because in this increase back, you also have these changes here. You have the block dim put in defines and so on. Again, now we can compile this increase back. If I write it correctly, increase back. And now you will see that there's a loop that is not vectorized because it still has the kubroot function, but there's another loop that has been vectorized. This is the loop that's below with the other part of the arithmetic. And the same with the loop that was not vectorizing before because of the indirect accesses. Now it's vectorized. You don't need to believe the compiler. You can believe RAVE. So we can do RAVE print rep. Let me go to the history. We can, let's call this increase back, and let's run the increase back binary. Now you can see that the volumes phase, which is this one, has vector instructions. This was a 0 before. This is now a 28%, or sorry, 26% vector instructions. Also the temperatures, this was a 7%, now it's a 25%. And then there's the pressures that is divided into the pressures kubroot, which has a 0%. We expected this because we cannot vectorize a function call. But the other part of the pressures has a very good number of vector instructions, which is nearly 30%. Of course, you can also look at this on Paraver. Let's wait for the trace to load, and we can see that the same thing that you can see in the log, but with a more visual approach. So here you have the vector mix. Let's open also the phase. Let's open the instruction timeline. This will be synchronized with one. This will be synchronized. And you can see, for example, let's zoom in a little bit. Let's zoom in a little bit more. You can see how now this red phase, which is volumes, it now has vector instruction, the same with all except the big blue guy, which is the cube root. Let me zoom in. This blue guy, which is the cube root function, all of the other rest of the program is vectorized. What else can you do with RAVE? You can study the vector length of the code. So let me open this average vector length per phase view. And let me zoom in a little bit more, a little bit more, and a little bit more. So what do we see here? These views are, again, aligned. You can see that there's a graph here. The higher the graph, this line is, the higher the vector length is. This is plotting bytes per vector. I told you before that we had 16,000 bits. This is 2,000 bytes per vector. And you can see, for example, that this dark red phase is at 1,000 bytes, more or less. The white phase temperatures go slowly. It goes here. And then for these two last parts, it moves a lot, but it's high again. You can also see this information on this table down here. This is the average vector length or average bytes per vector of each phase. This is saying that the temperature has an average of 256 bytes per instruction, volumes 1,000 to 200, and delta 1 a little bit more, and pressures back similar to volumes. So this is the second issue that we see with our code. Okay, we have managed to vectorize nearly all the phases, but we are expecting a higher vector length. Our accelerator can have 2,000 bits per vector. We want to use that bits. We don't want to use only 200 bytes. So allow me to go back to the slides for a moment. How do we increase the vector length? So the vector length is mainly limited by the innermost loops of the code. In our case, we have this kind of loops with go from j equal to 0 to j equal to m. M is hard-coded in our example to be 162. That's why we are not getting that higher vector length. Ideally, on the EPAC architecture, we would want loops to be at least 256 elements wide, so we can take advantage of the full register. One solution to increase the vector length without changing the program much is to, when you have this kind of matrix or 2D approach to operating elements, do 2 rows at a time, for example. So you increase the size of the innermost loop. Or you can go to the extreme and say, okay, let's execute all the rows in a single loop. So now the loop goes from 0 to n times m, and you can take advantage of the whole vector register much easier. We can apply this to pressures back, to volumes, and to delta, but the phase temperatures has another problem. It has a blocking structure, so this is very typical on codes that are intended to run on smaller vectors or with to utilize a type of cache or a specific size of a cache or something like that. So we cannot directly collapse the loops because we need to respect this blocking, and also because if I will show you the code again in a minute, but we were not accessing the elements on the edges of the array. We had kind of an stencil code. So we cannot easily collapse the loops because we need to skip some elements, and this complicates everything. So what we do for this tutorial is just let's increase the horizontal block size to at least cover a full row. Then let me show you on the actual code. So increase vector length. Here you can see that we have, let me make this a little bit bigger. We have collapsed the loops for the, this is for the delta, this is for the pressures, and here for the temperatures, this is what I meant with the, that we don't access the edge values on the array because we have this kind of stencil operation. But what we did was increase the horizontal block dimension. Okay, so we can compile this again, increase. And let me run the previous one for a second. This is not the one that I just compiled. This is the previous one, just so you can see that the vector length here is low. For example, for the temperatures, the average vector length is 32 elements. When we run the increase vector length, let me also name this increase vector length, you can see on the report that vector length was 32, now is 160 elements. Good news. For the pressures, for example, is now basically 256 elements. That's the maximum that we can get. So, of course, we can look at this information on Paraver, but it will just confirm what we just saw. We can go to the average vector length per phase. I can zoom in. I can zoom in a little bit more. And here you can see how now, if you remember, this line was much lower before. Now it's about halfway. And for these pressures and for the volumes and delta, the vector length is basically the maximum of the machine. You can see this also in the table, an average of 1,280 bytes per vector, and here it's closer to the 2,000 maximum of the machine. So what did we do until now? First, we just vectorized. We saw that some regions were not being vectorized, and we changed the code and the compiler and everything in order to make it vectorized. Then we saw that the vector length was very short on some phases, and we changed the code to make the vector length bigger. And then the next step that we can do is study what are the actual instructions that are being executed to see if they are what we should expect or not, if there is any problem there. So allow me to open another view, which is the instruction type count per phase. So I'm going to cheat a little bit because I already know the solution. But if we go to the volumes phase, what we see on this table is a recount of the instructions that are executed on the volumes phase. This is the red one here. You can see that we have some, this is a shift operation, these are some multiplications, some loads. There's an indexed load. This makes sense because the volumes had that indirection that I talked about before, scalars. But there are two guys here that do not belong. We have the vector widening at and the vector slide down. These two instructions are not doing any useful work. They normally appear when you are mixing different data types in the same code on the RISC-V vector specification that we are using. So this is computing, this is loading, but this is not computing. This should not be here. Of course, you might not know that, but once you get used to it, you will start to detect these weird instructions. So with RAVE, you can see them. If you go back to the slides, you will see that this is the volumes computation. This had that indirection that I talked about before. And what's happening here is that the volume is a double precision array, pressure is a double precision array, temperature is a double precision array, but the bounds, which is the index of the pressures, is a 32-bit array because they are integers. So the compiler is having a hard time, and the hardware is having a hard time mixing the data types, and it's needing to move bits up and down or around. So that's what's causing these instructions. What we recommend to do when you find this is put everything to either 32 or to 64. You will use more memory and all of that, but you will gain in the long run. With newer versions of the compiler and specifically newer versions of the hardware, this will not be needed. But for now, the best option is to just put an alias, a type def for the floating point and for integer, make them both 64 bits or 32 bits or whatever bits you want, and work with that. We have applied this to the code. Oops. Here on the flex data type, you can see that now you have this type def here, and the volumes array, the pressure array, everything is a parametric type, including this bounds array. We can compile this, flex data type, and we can run it with RAVE. Let's make this smaller. Flex data type, and let's call this flex. Again, this will run, and now, well, let me run the previous one before so you can see the report. We could also have seen, this is the volumes array. This is before applying the last fix. Here you can see that you have some instructions that are of 32 bits. This is CU32, and some instructions are 64 bits. That's what I meant when I said that we were mixing different data types. Now, with the new binary, if we run it and we go to the volumes, we only have 64-bit instructions. So instructions that each element of the vector has 64 bits. It has many more bits in the vector, but each element is 64-bit. Of course, we can, you already know what's coming now. We can open it in Paraver. And if we get the same view as before, which is the instruction type count per phase, and we go into the volumes function, now we don't have the instructions that I saw before that are the vector slide down and the widening. And here we just have computation, multiplications, loads, stores, and scalar instructions. Okay, so with this final optimization, the RAVE, the work that you can do with RAVE ends. Of course, you can look at other things like how many registers are being used, and then you can know if you can unroll your loops. You can look at the program counter to detect iterative patterns. You can do a lot of things, but for this tutorial, we just wanted to look at increasing the vectorization, increasing the vector length, and detecting and eliminating weird long latency instructions. Then there's a final part of the tutorial that I will not do live, but I want to show you since we have still time, I believe, which is running the code on the FPGA that has the hardware of the EPAC. So in this step, we can get timing measurements because until now, everything was emulation. We just saw instructions, but we did not see how fast we were going. Of course, less instructions in general means that you go faster, but it cannot be the case. So in this last step, I will just show you in the slides because doing this live would take us more time. But on our system, you can send jobs to the FPGA. We have a script that runs all the different versions that I just shown you. And let me show you this slide. Here you have the codes that I just shown you in the previous half an hour. So this is the reference code, so scalar code. This is vectorization without changing anything in the source code, just enable compiling vectorization, then increasing the vectorization of some phases that were not being vectorized, increasing the vector length, and then this data type at the end that reduces the number of weird instructions. Here you can see how just activating the vectorization, this is, of course, the time per iteration, so lower is better. You can see that just activating vectorization already gave us a 1.86 speedup. Again, this is running on an FPGA. This is cycle accurate. So this is as close to the actual hardware that you can get without spending $1 billion printing a silicon chip. And then you can see that as we increase the vectorization, we get more speed up. We increase the vector length, we get more speed up. And at the end, we get a little bit more of a speed up when we eliminate these useless instructions or weird instructions, up to a 4.22x speed up. Another thing that we can do with the FPGA is get other kind of traces that can also be open in Paraver, which are extract traces. You don't need to know this. I'm just going to show you. Let me show you this. Yeah, okay. So by now you are familiar more or less with this interface, but this is no longer a RAVE trace. This is an extract trace. So here you have actual execution time on the horizontal axis. These are the code faces. You already know the colors if you have been paying attention. And here you have tables with, for example, the average CPU cycles that each phase takes. So this kuberoot function, it's nearly 1 million cycles per zone. Temperatures is 100,000 and so on. You can see that most of the time is spent on the pressures array and pressures zone and on the volumes zone. The rest are not as time consuming. You can also see these numbers. This we already kind of seen. This is the vector mix. So percentage of instructions that are vector. So 20% of the instructions are vector, 17, 23, 26. This is the vector activity. There is something that you cannot see with RAVE, but you can see in the FPGA. This is how much, the percentage of time or the proportion of time that the vector unit is doing work. So what does this mean? 93, it means 93% of the time the vector unit is doing work. Let it be loading data or computing data or whatever, but it's active. You want this number to be as close to 1 as possible because that means that you're using the CPU that you paid for. And then we have a third number here. This is the vector CPI. CPI stands for cycles per instruction. I mentioned before that the vector length can change. So depending on the vector length, the instructions will take longer or shorter. Also, if an instruction goes to memory, it takes more time and all of that. So the higher the vector CPI is, the worse. So you want this to be as low as possible. And here what we just see is that the volumes phase has a very large vector CPI. This 300 means that for each vector instruction on this phase, on average, you take 300 CPU cycles to complete the instruction. This is a very big number. I will go briefly over this slide, but when you have indirect accesses like we do in the volumes, and we have a very large vector CPI, this normally means that you have a TLB issue. So you're having indirect accesses, which means that you are accessing one element that is in one point of the memory, one element that is in another completely different point of the memory, and everything is scattered around the memory. You rapidly run out of TLB entries to hold all of that information. So one thing that you can do is activate huge pages in the operating system. Huge pages are 2 megabytes instead of 4 kilobytes. So the probability of elements being on different pages is much, much, much smaller. I will not go into detail because we normally use these slides for a more in-depth tutorial, but you can activate huge pages in our system, get a trace again, and now the volumes went down from 4,000 cycles to 175 cycles, 1,000. And the vector CPI, if you remember, this was 300, now it's 130. Still high, but it's expected to be high because it has a lot of indirect accesses that, as I mentioned, are slow. So, but still it's a notable speed up. Finally, to end the tutorial, here you see the time per iteration that for the different versions. This last version is activating huge pages. So one takeaway, and this is the speed up, one takeaway from these plots is that up to this point, we got a 4x speed up just running on simulation. On my own laptop, paying virtually €0, I could get a 4x speed up without touching the accelerator. Then, thanks to having the hardware, we could see other kind of behaviors, and we could get a little bit more of performance. But just using RAVE, just using your laptop, you got a 4x speed up in your code. And of course, 4x or 5x for the last is high, but it's not impressively high. With GPUs, you can get much, much higher. But the reason is that most of the time now is being spent on this phase that I told you that it was not being vectorized because it has a function call. So if we wanted to further improve the code, touching these functions will not do much. We need to try to vectorize this function however we can. Okay, so of course, all of this is funded by the API project and these partners. So if you have any question about either about RAVE or about the infrastructure we have at BSC or about the EPAC chip or whatever, you can, of course, ask me now. We still have some minutes left, or you can contact me at my email. Thank you for your attention.
Thanks a lot, Pablo. It was really great presentation. And let's see if I have a question. Yeah, I agree with Paul. So a quick question: do you plan to somehow collect all the knowledge that you have kind of discussed here and ensure the code and the platform can do suggestions about improvement, like and automatically maybe eventually fix the code or provide the quick fixes for the code that's being analyzed?
Yes. So actually, let me see if I have it open, but the repo for the plugin is open, I would say. If not, you can send me an email and I can give you access. But here you have everything for RAVE, so you can run this on your laptop without problems. There's also a tutorial that I can also give. SDB, let me go here. There's also a tutorial with the same code that I just shown you. What is this? SDB vector analysis tutorial. Yeah. This is the code that I just shown you with all these steps and all this Paraver and all of that. All of this is already publicly available. So if anyone is interested, I can give you directions on that. So yes, I don't know if this was the question, but this is open. You can try to replicate it on your laptop and try to improve it and propose new functionalities and all of that. Yeah, I would be very happy to have feedback.
Great. So folks, if you want to ask questions verbally, just let me know. Raise your virtual hand and I can allow you to speak, or put your question in the chat. Or otherwise, you can. I'm going to share. You can share his contact, and you can, of course, get in touch with him directly. Questions? Looks like we do not have any at this point. So I'd say, given the quality of the presentation, maybe you have answered a lot of the questions. So thanks for that. So thanks very much, Pablo. Thanks for presenting. Thanks for explain all these details and show the performance that we can have. I'll be using the tool. The recording will be available on our RISC-V YouTube channel the next few days. And yeah, so if you have any other presentation that you'd like to share with us, so feel free to reach out and we can schedule another tech session.
Sure. Thank you very much for having me and for inviting me to the technical session.
Sure. Thank you very much, folks, for attending. Thanks very much, Pablo, for presenting. See you all, folks, in the next one.
Bye, everyone.